sono molto contento di avervi qua. Siamo pochini ma buoni, come si suol dire. Ringrazio il professor José Tadeu Lunardi dell'Università Statale di Ponta Grossa, Brasile. Lui farà una presentazione dal titolo Point Interactions in 1D Relativistic Quantum Mechanics, Physical Parameters and Symmetries. Poi comincia Tadeu. Eccoci, allora Tadeu comincia.
Allora, buongiorno a tutti, io vado a fare un saluto in italiano e poi parlo in inglese.
Benissimo.
Io ringrazio tantissimo per l'invito di Silvestre e Fabio e tutta la cortesia, la gentilezza da loro dimostrata. E per me è un piacere essere qui alla Unimar Marconi per fare questa presentazione e saluto pure Manolo, Luis Miguel, che sono in collegamento. Ok, let's start our presentation. I will present today some of our recent results on point interactions in quantum mechanics. My talk today will be on the I will speak about one point interaction in relativistic quantum mechanics based on the Dirac equation. And at the end, I will speak about some results about 2-point interactions, a double point barrier. Okay, this work is being done in collaboration with my colleague from Concordia College in United States, Luis Manzoni, and my colleague from my university, Carlos Bonin. Well, this is a brief outline of my presentation. I will make a brief introduction about point interactions. I will present our approach to these problems, which is based on the Schwartz theory of distributions that we call the distributional approach. And after, I will show how to obtain the parameters that features these interactions in terms of most physical parameters. After, I will speak about how to study symmetries, basically the symmetry under parity, by using these parameters. And at the end, I will present some discussions and suggestions for further studies. Well, point interactions in one dimension are used in several models involving idealization of short-range interactions. For example, the Krieg-Pini model for a particle in one-dimensional lattice, the Lieb-Liniger model for one-dimensional gas, etc. And apart from these applications, point interactions also serve as a theoretical laboratory to investigate some methods of quantum field theory, mainly regularization and renormalization techniques. And in quantum mechanics, we have a much simpler model, and this can teach us some things about more complicated models, as in quantum field theory, for example, where regularization and renormalization is a ubiquitous technique. Then point interactions in one dimension, contrary of what could appear, are richer than in higher ones because it allows a larger variety of interactions, as we will see. Well, physicists normally use regularization and renormalization techniques to obtain singular interactions as a limit of a sequence of regular ones. This works well, for example, to define a Dirac delta interaction described by a potential of kind of a Dirac delta. we can start, for example, for a rectangular barrier and make some limit with the base shrinking and the height going to infinity. This is very well known. However, these procedures can lead to ambiguities in some cases, with the result depending on the limiting procedure. For instance, there are issues regarding a proper definition of an interaction to be associated with the odd point interaction given by the odd delta derivative of the Dirac delta distribution. The derivative of a delta distribution is a odd distribution. It's odd under parity. And if we simply put this in the Schrödinger or basically the Schrödinger equation, this can lead to ambiguities of how to define the products of the wave function, and this distribution is not so simple as in the case of a Dirac delta, that we can do that with some alchemy and we can define that interaction. But with the derivative of a delta distribution, this is not so simple. Mathematically, this problem is solved within the approach of self-adjoint extensions of symmetric operators. We will call this SAE, from which it emerges a family of 4 parameters for the admissible point interactions. In the self-adjoint extensions approach, the potential at the singular point has no meaning. Only the Wall Hamiltonian has a sense as a self-adjoint operator in the Hilbert space. All the properties of the interaction are encoded in the boundary conditions the wave function must satisfy at the singularity. Then there is no sense to speak of what has at the singularity. We simply put out the singular point and study the systems through its boundary conditions. An issue related to the above feature of these self-adjoint extensions is the difficulty to characterize a point interaction which be odd under parity, which should play the role of interaction associated, for example, to a singular potential described by a Dirac delta derivative, because we don't have information about the details of the interaction beyond its boundary conditions. From a physicist's point of view, it would be interesting to have some intuition about the properties of the interaction itself, since in real applications we have actually short range potentials, being the singular points just mathematical idealizations. Well, in this talk we will present a brief outline of our distributional approach, but now applied to one-dimensional Dirac equation with point interactions. We have presented some sketch of this method to the Dirac equation in one paper of us published in 2014. But now we have learned somewhat more about this problem. And in that paper, we have concluded that there was no odd interaction in one-dimensional Schrödinger or Dirac equation that was odd. And now, with our last results, we should correct this claim, because now we have a path to characterize odd point interactions. Well, then with this distributional approach, we will obtain an explicit distribution for the interaction term without involving regularizations. And this distribution will give the same family of 4 parameters interactions found by the self-adjoint extensions method. A covariant way to write the interaction distribution in a way that the 4 parameters can be identified to physical parameters, usually associated to point potentials. Then, in this talk, we will present this way to associate the 4 parameters. Because the Selfadjoint extensions establishes the solution as a form 4-parameter family, but the physical meaning of those parameters are not very clear. Then in this work, we intend to make a connection to more physical parameters. And then I will present a more intuitive and we claim correct way to characterize the interaction symmetries. In particular, we revisit the issue of characterizing point interactions according to parity. Especially, we will deal with odd interactions and correct our previous claim in 2014. And finally, I will present a discussion on the admissible arrangements with even and odd parity for double point interactions. All this approach for one singular point can be straightforwardly extended to more point interactions, and I will speak a bit about the 2-point interactions. Well, let's start with some ideas from our distribution approach. It's important to note first that there are some proposals of distributional approach to lead with point interactions. One famous work is from Kurasov, but Kurasov used a non-standard theory of distributions, what he called distributions on discontinuous test functions. It's important to emphasize that all our work here is based on the standard Schwarz theory of distributions. Well, the one-dimensional Dirac equation in the presence of the most general external regular potential, here we are not speaking about singular potential for this moment, is defined as a term that I am calling S-reg, the regular of regular, S-psi, where this S-regular is given in terms of scalar, vector, and pseudo-vector potentials. In 2 dimensions, we can associate the gamma matrix with the Pauli spin matrix with the definition of the gamma 5 as gamma 0, gamma 1, which is equal to the sigma 1 Pauli matrix. And the metric we are using are the diagonal 1 minus 1. Okay. Well, the interaction term in the Dirac equation, as I said, is that product of a term which I call S-reg with the wave function, which is the Dirac spinor. And this term, as it is explicitly shown in 3, involves multiplications between the potentials and the wave function, the Dirac spinor. We are interested in the case in which the interaction vanishes everywhere, except in a countable set of points sigma in the real line. Also, we assume that there is a special Lorentz frame, the lab frame, in which the singular points are fixed in the real line. Potentials associated to this kind of interactions are usually described in terms of the Dirac delta distributions and or its derivatives. However, and here is the problem, in the Schwarz theory of distributions, multiplications involving distributions are an issue and are not universally defined. Just in some special cases, we can define the product of two distributions. For instance, when one of the distributions in the product is a infinitely smooth function, or some other special particular cases. But in general, a universal product of two distributions cannot be defined in the theory of distributions. And this is the source of many of the infinities that arise, for example, in quantum field theory, where we take naively products of distributions which are not well defined. And this requires us after to make some regularizations, to define those products, and to make renormalizations and subtract infinities. And this is, like Feynman said, and it's to put the dirt below the tapet, and under the tapet. It's a sort of alchemy to fix the mathematics in the middle of the way and not depart from very well established principles. But there are other approaches, even in quantum field theory, that uses distribution theory. One of the most known is the Epstein-Glaser, Bogoliubov, Epstein-Glaser causal method that uses theory of distributions. And what we do here with theory of distributions is inspired by our previous experience with the Epstein-Glaser method. Well, potentials are associated. Okay. I come back here. Okay. From what we said, the interaction term in the Dirac equation, in the right-hand side of the Dirac equation, loses mathematical sense if we simply substitute the field potentials in the multiplication by their associated point potentials, because we have a product involving at least one singular distribution. Well, our distributional approach begins by considering the Dirac equation, or also the Schrödinger equation, in the sense of distributions. Namely, the potential and the wave function will be considered as distributions, and the derivatives must be understood in the distributional sense. Then we can speak about derivatives of Heaviside thetas, deltas, Dirac delta, first derivative of Dirac deltas, etc. In theory, in Schwarz's theory of distributions, the distributions are infinitely differentiable. Since the product of two arbitrary distributions is not defined in the theory of distributions, the interaction term in the Dirac equation must be replaced by a suitable, well-defined distribution, satisfying very basic requirements. Well, then we will replace this ill-defined product in the right-hand side of the Dirac equation by a distribution that I am calling delta, which may depend on psi and the coordinates, like the regular case. In order to determine this distribution, we will first work in the lab frame, where the Dirac equation is separable and appears as in the form 5. Here we have separated the variables in the usual form. The psi, the caps psi is writing in terms of the position, a time-independent function, the small psi, and multiplied by the temporal evolution within a fixed energy. And also the delta interaction term will factorize, because we are assuming that in the lab frame the point interactions are fixed and not time independent, not time dependent. Well, and to determine this distribution, interaction distribution, we will require it to satisfy very basic requirements that I will present below. Here I am abusing a bit of notation because we are working with the time independent equations. We are simply now using the notation X for the special component of the 2 vector. The first requirement is a very, very, very elementary one, and it requires that the distribution must be defined on the entire real line and must coincide with a regular product in all the intervals where we have not the singular point, on real minus the set of singular points. Distributions, just to recall, are not defined at points. Distributions must be defined in intervals. When I say that the distribution must be defined on the entire real line, it means that the test functions on which they are applied must be defined on the entire real line. The second requirement is that the wave function must correspond to a regular distribution. This means that it must be locally integral in the Lebesgue sense. Thus, this fixes the singular order of the wave function. This fixes a bound for the singular order of the wave function to be at most -1. Here I am using the concept of singular order of a distribution according to the book of Zemanian, because there are some differences in the literature to define the singular order or the order of a distribution. With the definition, with the Zemanian's definition, we have that, for example, the delta distribution has order 0, its derivatives order 1, 2, 3, etc. The half side theta, which is a primitive of the delta distribution, has order -1, etc. And -2 corresponds to a distribution that is equivalent to a continuous but not differentiable function. Then every time we take a primitive, we lower the singular order, and every time we take a derivative, we higher the singular order. Then to be a locally integrable distribution, it must have at most the singular order -1. This is, for example, to prevent that the stationary wave function have a Dirac delta, and in this way it will not be locally integrable. Distributions that are not locally integrable, that not correspond to local integrable functions, are said to be singular. Regular distributions are...
Now, if I may try to explain the concept of singular order in more physical terms, essentially the delta has singular order 0 because in p-space it is a bounded function. The delta prime has singular order +1 because in p-space it is given by the function P. So essentially, that is what you're telling us. And by the way, these concepts make me feel a lot of nostalgia for my old times in Zurich, when I worked for 3 years with Professor Schaff and maybe with Walter Brzezinski, a great Swiss-Brazilian physicist. So I feel a lot of nostalgia because that was 30 years ago.
Yes, I read some works of them. Ginter Scharf, it's a very good book on the Epstein laser applied to QED.
Yes, the causal approach to quantum electrodynamics.
Yeah. Okay. Then,
yes.
And the last requirement is that the interaction distribution must be such that the current density is conserved across the singular points. And this is a physical requirement that leads after to the conservation of probability.
And equivalent to the Selfadjoint of the Hamiltonian.
Excuse me?
This implies the Selfadjointness of the Hamiltonian.
We can't understand. It's not clear what you are saying.
No, you see, you have a Hamiltonian, a Selfadjoint Hamiltonian, which is the Dirac Hamiltonian with interaction. And this Hamiltonian, Dirac Hamiltonian with the interaction, if the current density is conserved, this guarantees the self-adjointness.
Yes.
Okay.
What I will show is that with these simple requirements, we will obtain exactly the same results as the self-adjoint extensions of the Hamiltonian with point interactions. This last requirement is what links obviously the two approaches. We will obtain exactly the same boundary conditions, and as I will show, these boundary conditions determines completely the interaction distribution. Just what our method provides is a plus, which because it shows what is in this singular point, and knowing the structure of the interaction distribution, we will be able to investigate, for example, in a more natural way, the symmetries of the problem. Okay, as I was saying, as we will show, this set of requirements just presented reduce drastically the possibilities for the interaction distribution. Requirements are two, that of the singular about the singular order, sets also an upper bound to the singular order of the interaction distribution. By imbalancing, equalizing the singular orders in both the sides of the Dirac equation, we conclude that the singular order of the interaction distribution must equals the singular order of the derivative of the wave function, and this must be less than or equal 0. It will be less than 0 if we're not point interactions. We start by considering an interaction that vanishes in all points except the origin. Therefore, our interaction distribution is a singular distribution that coincides with the zero distribution in any interval that does not contain the origin. In the language of distributions, D is said to be a distribution with support concentrated at the origin. To deal with the requirement R1, that says that it must coincide with a regular outside the origin, and that it must be therefore a singular distribution with support concentrate at the origin, we will state the following theorem from the book of Zimanian. It says that a necessary and sufficient condition for a distribution F on R to have a support concentrated at the origin is that it must be a finite sum of Dirac delta and its derivatives until the order of the distribution F, where these alpha m are constant coefficients. The above theorem, together with requirements of the maximum singular order of the wave function, and that sets a maximum order for the interaction distribution, implies that the interaction distribution must have the form of a constant coefficient multiplied by a delta, a Dirac delta distribution. That omega psi is a number, is not a function. Is a number that depends on psi. Then it is a functional of the spinor psi. This omega in Dirac theory are two 2x1 matrices whose entries are complex numbers that may have a functional dependence on the spinor psi. A complete specification of this coefficient will completely specify the interaction. Well, and our strategy...
Tadeu, I'm sorry. Expression 7 completely defined the possible interaction. Expression 7, you mean?
See?
Okay. The interaction is completely defined by the expression 7.
Yes.
It's unique, okay, in this sense. Okay, thanks. Okay.
Once we find omega, it is defined, yes. Well, our strategy to find omega will be first to take the distributional indefinite integral in the Dirac equation, that one here, 4. Then we will take the indefinite integral for not this 5 stationary. And we obtain this result. In the right-hand side, the primitive of the delta distribution will be a heavy side theta, and there is also, in the theory of distributions, a constant C after the primitivation, and this constant is a 2x1 column matrix. Now, psi minus 1 is a primitive of the Dirac spinor. It must have singular order at most minus 2, because psi has singular order bounded to minus 1. And we have that this is a continuous, in the distributional sense, at the origin, as I mentioned earlier. Since the right-hand side of 8 has finite lateral limits around the origin, because it is just essentially a theta function, theta distribution, we conclude that psi must have finite lateral limits at the origin 2, because the second term in the left-hand side is continuous. Then if the right-hand side have finite lateral limits, then the psi, the first term in the left-hand side, must have finite limits too. By taking then the lateral limits around the origin, 0 plus and 0 minus, and subtracting the results, we obtain a relationship between the omega, which defines the singular interaction, and the difference of the Dirac spinor in both sides the origin. I will call this relation a boundary condition relationship. From this result, we conclude that there is a one-to-one correspondence between the boundary conditions at the origin and the interaction distribution. Once we know the interaction distributions, we can establish the boundary conditions and vice versa. We shall obtain now all the admissible boundary conditions at the origin by using requirement R3, not R2, R3, namely the current conservation across a singular point. And this part of the computations is made in several papers, which obtains the matrix lambda or separated solutions by imposing current conservation. Well, current conservation across the origin means that the current at the left must equals the current at the right, and all these terms in this equation are well defined because the wave function has well defined lateral limits around the origin. And we define these two column vectors, V1, V2, in the way we show here. And in terms of these column vectors, current conservation amounts that the norm of these column vectors, defined in the usual way, must be preserved. This is the last equation. And thus, this implies that there exists a unitary matrix U that relates vectors common matrix V1 and V2. Then we can rewrite the boundary conditions in terms of V1 and V2, and we can express the matrix omega in terms of these quantities. From the above, all the admissible point interactions at the origin form a family of 4 parameters, which are the independent real parameters of the unitary matrix U, and can be expressed in this form. I have just written omega as I gamma 1 psi plus minus psi minus, and rewriting psi plus minus psi minus using the vectors, the matrix V1, etc. And I have obtained the last expressions, which includes the matrix, the unitary matrix U with his 4 independent real parameters, which can be written in terms of 4 real independent parameters. We denote, as usual, the unitary matrix U in this form, where by the conditions its element must satisfy has obviously 4 real independent parameters. Here, if we put z equals 0, it will correspond to impermeable interactions, or also called impenetrable barriers at the origin, and this will separate the solutions in the right and the left side. And we are not considering this kind of interactions here. We will consider just the interactions which does not separate the solutions, And in this case, we can find reparameterizing the interaction to obtain a matrix that connects the solutions on both sides. This is the well-known lambda matrix, right? In terms of a phase phi, and the four parameters, real parameters A, B, C, and D. And these parameters must satisfy, I forgot to write here, A, B minus C, AD minus CB equals 1. The determinant apart from the phase factor is 1. In terms of this connection matrix, the interaction distribution can be written in this form, where we can use write in terms of psi0 minus or psi0 plus. This is nothing more than I gamma 1 psi0 plus minus psi0 minus. And then we substitute psi0 plus for psi0 minus using the connection lambda matrix or vice versa. Since these parameters of the lambda matrix have no direct physical interpretation, in the above form, it's a difficult task to study important features of an interaction, as its symmetries, for instance. Therefore, it's desirable to write the interaction in a form to put in evidence its physical parameters and after to explore its symmetries. Before to go forward, I recall that all these results are obtained in the self-adjoint extensions, are not new. What we are presenting here is that our distributional approach leads to the same results, but with a specification of a distribution at the origin. Just not substituting the origin as a black box with only the boundary conditions. Well, now it's desirable to write the interaction in a form to put in evidence its physical parameters, and after using these physical parameters to explore its physical symmetries. Since the interaction is completely determined by the difference between the wave function on both sides of the origin, I commit a misprint there, psi0 plus minus psi0 minus. We will rewrite these values of the spinors at the both sides at the origin in a way that it separates the even and the odd contributions of these combinations. Now we substitute this expression into this to one of these equations, and the results are exactly the same if I substitute in the other. We obtain this relation 18. Then, in principle, we would like to isolate the omega to write the interaction. But I can only have unique solutions for omega if that condition 19 is satisfied. As we will show later, this condition will ensure, for example, that all the physical parameters be finite. Because we can study how the physical parameters behaves as these terms tends to 0, and some of them or all of them goes to infinity. Then this restriction is to make physical finite parameters. Then with this condition,
What was the notation? Phi was the, oh, sorry, just confused about the notation now. Phi was the face of the matrix lambda, A and D were the diagonal entries?
Yes.
Okay.
The main diagonal AD, and phi is the phase. Then, with this condition, we can solve the last equation for omega, reorganize the results, and write then using the Pauli matrix basis together with the identity. And this forms a basis for the gamma matrix as well. And then we rewrite the terms involving the lambda matrix in this equation in red by using the gamma matrices and the identity basis. Well, here we stress that this expression remembers that the case we had with regular potentials. The terms in red are basically similar to the potential, and the term in blue substitutes the wave function. Here, remember that the interaction distribution is omega times delta Dirac. Then, when we put delta Dirac inside with this red term, we would have a term that plays the role of the potential, the potential function, but not the potential distribution. All these terms here in 20 are numbers, not distributions, are just numbers because omega is a constant matrix. Well, here, to make this identification of B, A, Mi, and W physical quantities, we identified in the expansion of that term in terms of the gamma basis, we make the identifications number 21 to 24. Then we see that previous conditions of non-zero for 2 cosines phi plus D plus A is just to make these quantities finite. Well, now the complete interaction term, as I said, can be written in this form. In analogy with the regular case, we call the term in red as the singular point potential, and the real constants B, Mi, and W as the potential strengths. Then, for example, B delta X will be the potential, the pseudo scalar potential field, and B is the potential strength. Returning the temporal dependence in the lab frame, we can rewrite the Dirac equation with the above interaction term in a manifestly covariant form. And this is easy, is just by multiplying by the time factor, which has no singularity. And I think this is a somewhat trivial task. And we can write the relativistic Dirac equation in the form 28, where now psi is the complete Dirac spinor with the time dependence. And in this form, it's manifestly covariant. Then this is valid for any Lorentz frame. Mm-hmm. And here, the point, the singular point now is represented by a word line. In the lab frame is a vertical line, and for any other Lorentz flame, it will be aligned with a slope. And the localization in the Minkowski plane of the singularity is given by the argument of delta distribution going to 0. And the boundary conditions will be associated with the values on both sides of this word line. Since the Dirichlet equation, the last one, has been casted in a manifestly covariant form, as I said, it holds in any Lorentz frame, given that the potential strengths B, M, and W appearing in the interaction term transforms respectively as a scalar, two-vector, and pseudo-scalar under Lorentz transformations. Well, this last equation can be viewed as the correct form to interpret the ill-defined multiplication of a singular point potential to the wave function. Then here we cannot simply multiply that singular potential with the wave function in the past, naively. But this result 28 shows us how to interpret correctly that interaction term that in the regular case is just a multiplication. Here we must multiply this potential distribution with that combination of the wave function. Now we can invert the relations associating singular the potential strengths to the parameters of the boundary matrix lambda. We can invert that relation. It's a non-linear relation. It's not so simple to invert, but we make several other procedures. We can to express the terms of the lambda matrix now in terms of the physical parameters, and the result is this. Then, for example, the phase parameters of the lambda matrix is the argument of this combination of the fields, this complex combination of the fields. Here is just the absolute value of this complex number. And here, this term divided by this absolute value is the parameter A, and etc. Then we were able to express the boundary conditions matrix lambda in terms of the physical parameters. Now we can study some symmetries, and we will concern us here with the parity transformations, by taking advantage of this identification of the physical parameters. Just recalling, under spatial reflections, the space-time coordinates in the Dirac fields transforms in the usual form. The operator of parity is the matrix gamma 0, and the transformed wave function will invert, and psi plus goes to psi minus, etc. And the potential distribution, singular potential distribution, also transform accordingly. And we observe, as usual, that the strengths associated with the scalar and time component of the vector are invariant under parity, and the space component of the vector and the pseudo vector changes sigma. Then here in this result, we use the fact that the delta distribution is an even distribution. Even distributions are defined in the theory of distributions as those distributions invariant under space reflections, argument reflections like in this case, and the even are changes sign. And the delta is an even distribution. And here is the this argument of the delta when it's equal to 0. It identifies the singularity, but as delta is an even distribution, this is invariant. Then the only effect of the parity transformation is to exchange A1 to minus A1 and W to minus W. From the above, as expected, the strings B and A0 are parity invariants, even, and A1 and W are odd under parity. Collecting the above results, we have that the whole interaction distribution transforms under parity in this form. In the lab frame, in the stationary case, this can be written in this last form. We will come back to the lab frame to make computations several times because it's easier. We go to a general Lorentz frame just to interpret that terms as according to their Lorentz transformation properties. And now we can, with these results, study what it means to have an even or odd point interaction. Interactions here. When the potential is described by a regular function, the interaction is said to be eventually even or odd according to the parity of that regular function describing it. Another way of defining the parity of a regular interaction is by saying that the interaction is even if the transformed wave function satisfies the same Dirac equation as psi, and that the interaction is odd if psi transformed satisfies a similar equation, but with the potential inverted. Then we can define even interactions without making reference to the potential, but it enough to say that the transformed solution satisfies exactly the same equation. But when we talk about odd interactions, we cannot say that without making reference to the potential, because the transformed wave function must satisfy the same equation apart from the inversion of the potential. And how to formulate this without knowing the details, the idea, the notion of a potential. In self-adjoint extensions, we don't have this notion anymore, because, as I said, the interaction is enclosed in a black box. We only know what happens outside, but not inside. What is the potential describing that interaction? Then we find hard to give a sense, a meaning to the concept of odd interactions without making reference to the potentials. As I said, when a point interaction is specified only by the boundary conditions, like in self-adjoint extensions, we do not have information about the parity of the potential. But by using the second definition above, we can still define unambiguously the concept of an even interaction, but not of an odd interaction. On the other hand, a clear way to define the meaning of an odd interaction does not seem to exist for a point interaction. I don't know. Since in this case, also in the second definition, we need the concept of a potential. For instance, there are several unequivalent proposals for a point interaction which would be associated to a potential described by the derivative of a delta distribution. The derivative of a delta distribution is an odd distribution. It should describe an odd potential and thus an odd interaction. But there are several different and unequivalent proposals for distributions. There is one called delta prime, which is not to be confused with the derivative of the delta, because this is, for instance, an even interaction, and other proposals as the delta 1 by Albeverio Kurasov. Below, we will define naturally the parity of a point interaction by extending the properties of the regular interaction term to the singular case. We will state the definitions in the lab frame, and in the stationary case, the extensions to the time-dependent case, and for any Lorentz frame, follows straightforwardly. In the definitions below, the interaction distributions this symbol stands for a regular or a singular distribution, and S is the associated regular or singular potential. Thus, then I will define what it means for even and odd interactions in the regular case and simply extend this to the language of singular interaction, because we will set these definitions in terms of the interaction term. It does not matter if it's a regular or singular, because now we have an interaction term also for singular interactions. Then we define even interactions as an interaction whose interaction term is invariant under space inversions. And this is equivalent to require the invariance of the potential term. From our previous results, the family of even point interactions is a subfamily of all possible interactions. It's a two parameters family characterized by having A1 and W equals 0. Then even point interactions may be built just by using the first component of the vector field.
Because they change the sign.
Yeah, yes, exactly. When we
A1 is -1, A1, W is minus
exactly.
W.
To be invariant,
To be invariant,
term,
space transformation. Okay.
Exactly. And read in terms of the parameters of the lambda matrix, this implies that the parameters in the diagonal of the lambda matrix must be the same, and the phase must be 0. As examples of even point interactions, we have the so-called equal mixing of scalar and vector potentials, B equals 80, and the inverted mixing, B equals -80, whose lambda matrix are given by the forms here. For later, I will show the connections between the relationships between the relativistic and non-relativistic lambda matrix, and they are essentially the same, apart from some coefficients of 2 times the mass. And we can see from now that the first one corresponds in the Schrödinger case to a delta interaction, and the second one corresponds in the non-relativistic case to the so-called delta prime interaction. And now we can see that the delta prime is an even interaction. This result was also being observed by other authors in the case of even interactions. Even interactions were not difficult to characterize even without the knowledge of the potential, as I mentioned. The novelty here is to characterize odd interactions. And naturally, odd interactions are those that are odd under space inversions. Now, here, this definition appears very trivial. And equivalently, the potential term is odd under parity. And this will imply that the A0 and B components be 0, and we can have only A1, A, or W parameters. In terms of the parameters of the lambda matrix, this implies that B and C must be 0, and A must be the inverse of D. And phi, the phase, can be arbitrary. Then we have a 2 parameters family, subfamily of odd interactions. As examples, how many times more or less?
Because Silvestro must talk, let's say 10 minutes, 10, 15 minutes. Okay? Okay, thanks.
As examples of odd point interactions, we construct a pure pseudoscalar one that obtains setting A1 equals 0, and a pure gauge one setting W equals 0. And we obtain a pure pseudoscalar interaction in this form, only diagonal terms, and this pure gauge is basically the identity matrix with a phase, where this phase is given in terms of the pure gauge field in this form. And this first interaction in the non-relativistic limit corresponds to the so-called delta 1 interaction.
Sorry, Tadeo. The phase is the argument of 4 minus A1 minus 4I A1. And A1 in this case must not be equal 0.
No. Here is the set.
The gauge.
Is the gauge.
The
yes,
gauge,
yes,
not equal 0.
Here, W is 0.
W.
Yes. In this first, A1 is 0. In
okay,
this
okay.
second, they are
Okay.
to limit cases. Okay. Now, just to make the connections with these interactions we obtained in the relativistic case to the most known cases in most studied cases in the non-relativistic limit, I just will present how these interactions appear. Then in the non-relativistic limit, we also have a lambda matrix that connects the wave function and its derivative in both sides of the origin. I'm denoting the parameters of the lambda matrix with this subscript n. And here are the relations. Basically, as I mentioned earlier, they are practically the same with just these factors 2m. Well, the two examples I give of even interactions, as I mentioned, reduce to the so-called delta delta and the delta prime interactions. In the relativistic case, they are the equal mixing and the inverted mixing. And the non-relativistic case, they are called the delta and delta prime interactions. And they are both even. It's interesting to observe that originally the delta prime was devised to mimic an interaction associated to the derivative of a Dirac delta. And the fact that it results in an even interaction was somewhat unexpected. In the literature, the pure scalar interaction was introduced without this name from another arguments. Until I know, it was introduced by Albeverio and Kurasov. And it was argued that it has better properties to be associated to the actual derivative of a Dirac delta. They studied symmetries, but symmetries, scaling symmetries, not the parity symmetry. And they argued that this new kind of delta 1 is, in some respects, a better mimic to the derivative of a delta interaction. Our results corroborate these claims, but now emphasizing that it is actually an odd interaction of singular order plus 1 in the non-relativistic case. Even if it is no unique, one can have other combinations of the parameters W and A1 and create other odd with order plus 1 in non-relativistic quantum mechanics as well. The pure scalar interaction seems to be an interaction naturally related to the derivative of the Dirac delta, in the sense that in the non-relativistic limit, the Dirac equation can be rewritten in terms of the upper component of the Dirac spinor in this way. This is a Schrödinger equation. And here, this form resembles very much what would we have if the wave function were not discontinuous. If the wave function were continuous and differentiable, we would expect this equation here at the end of the slides. This is a result from the theory of distributions. And basically, what our results are showing is that for the pseudoscalar interaction, the upper equation is just the lower one with the wave function and its first derivative at the origin being replaced by the average of the boundary values around the origin, as it is the interaction term obtained from our method.
You mean the boundary condition characterize the delta and delta prime interaction?
Excuse me?
The boundary condition over in some way characterize the delta and delta prime interaction.
Exactly.
Okay.
But here this is an actual derivative of the delta.
The delta, yeah.
Interaction. This term here. And this characterizes the delta 1, not the delta prime interaction, the so-called delta prime.
Because you have delta x and delta prime.
Yes.
Okay.
This is the pseudoscalar that characterizes that with only diagonal terms. The definition, now let me discuss some of the results briefly. The definition of pointed distributions with definite parity, even or odd, can be straightforwardly extended to a set of singular points. In particular, we are at the moment studying all the admissible arrangements of two-point interactions with definite parities. In particular, we studied, following the ideas from Seba, the limits when the distance between the barriers vanishes. We obtained the following preliminary results for even arrangements of two single arbitrary interactions. When we shrink the inter-barrier distance and when the whole arrangement is even, we obtain always an even interaction. But when this arbitrary interaction, this is a subcase, are odd, we obtain the free case. Then the free case cannot be said to be even or odd. Okay? Then
But admissible means that they respect the requirements 1, 2, 3 that you
yes,
showed us
here,
at the beginning.
yes. And they respect the definitions we give for even and odd interactions. And when we make odd arrangements of two single even interactions, for example, we can make a delta, another delta, two single even interactions, but make an odd arrangements of the two, we obtain no interactions when we shrink the interdistance. When we make odd arrangements of two single odd interactions, we obtain an odd interaction at the shrinking point. And when we make odd arrangements of two single interactions with no defined parities, we obtain an odd interaction at shrinking point in some cases, and with no defined parity in other cases. Then there are two situations here. We have also studied the above limits with renormalized delta lambda parameters. I'm avoiding here to use strength parameters, renormalization in the strength parameters like SEBA uses, because we have associated strength parameters to the physical ones. Then I'm saying renormalize lambda parameters. Then I have studied these limits for some odd arrangements of two single even interactions, just this case. We studied the case where the single interactions were the equal mixing and the invert mixing present before. The renormalization was taken by multiplying the single parameter that reminds of this by the factor L minus N, where L is the interbarrier distance, and we studied the behavior of this renormalization varying N. An outline of these results valid for the two case studies are that for N less than a half, the limit converges for the free case, like the results of SEBA in some particular case with Schrödinger equation. For N equals half, the limit converges to a non-admissible point interaction in the sense that some of the parameters of lambda depend on energy. This is a result from for the relativistic case. In the non-relativistic case, this converges to a common delta interaction. We show then, therefore, that the non-relativistic limit and the L to 0 limit does not commute. And for N equals, for N greater than half, the limit results in an impenetrable barrier at shrinking point in all the case. And then here, just to discuss later in the next days or weeks, some future perspectives, it may be interesting to seek for some particular physical symmetries that could be able to restrict the family of point interactions still more until that just one parameter remains. Instead of starting the interaction, in particular one parameter interactions should be associated with a set of symmetries. Which symmetries? One issue that still remains open to us concerns the relevance or not of the phase parameter phi in the lambda parameters, and this parameter is strongly related to the relevance or not of the physical strength A1, the gauge potential. In particular, in our studies, until now, we did not succeed in interpreting these parameters A1 as being just a gauge, as often stated in the literature. In particular, we did not succeed in finding a unitary transformation with a discrete phase that leaves the Dirac equation with a general point interaction invariant. When we have the free case, it seems to be some sort of a discrete gauge transformation that makes A1 to appear. But when other terms like B or W are present, this discrete phase transformation seems to rescale all these other parameters. Then for us, this we don't know what is happening here. And in the case for us, it's not very clear in all the papers that say that the phase is irrelevant. There are some controversial issues there. For us, it is not clear that it will be solved. We may further the studies of bound states, resonance, tunneling time, etc., in the context of some special cases of the general relativistic arrangements of double point interactions with a well-defined parity, or use the non-relativistic limit of such arrangements to study the corresponding problems in non-relativistic quantum mechanics. And one thing I guess, in the Selfadjoint extensions method, the Hamiltonian has a meaning as a wall, as an operator on some domain in the Hilbert space, L2. It would be interesting to investigate if it is possible to give a sense for the kinetic and the potential terms separately, because we have two terms described by two distributions, separate in terms of distributions. It may be interesting to investigate the possibilities to formulate this approach in the framework of the rigged Hilbert spaces, which includes distributions as an extension of the usual Hilbert space. Thank you very much for the patience.
Grazie Taddeo. Adesso let's start speaking Italian or Spanish. Ok, non so se ci sono domande, ma penso di sì da parte del gruppo spagnolo o di Silvestro, perché credo è molto interessante le argomentazioni portate da... Ops, abbiamo un effetto di risonanza, appunto. E quindi non so se qualcuno vuole intervenire con delle domande a Taddeo, sono benvenute. Any question?
Well, as I said before, I like this approach because it reminds me of Professor Scharf's approach to quantum electrodynamics based on causality. So when you rigorously analyze the singular order of various distributions, so it's slightly complicated, but it's quite rigorous. So I like this approach.
Me too.
In my opinion, this talk has been very inspiring, and in particularly in the last transparency, there are some suggestions for further work, and I think we should carry out these suggestions so that Taddeo, in your next visit to Valladolid in 10 days, we will start with this.
Okay.
Ti aspettano per discutere appunto questa cosa insieme.
Sono molto motivato a visitarci.
Ok, allora non so se Luis Miguel ha qualche domanda.
Sorry.
No,
My
nessun
secretary
problema.
was phoning me I think it is quite interesting, the approach you have shown me. And indeed, I was thinking while you were talking in the application to some problems that you just mentioned in the almost the last transparency. So I think that this is, from my point of view, this is what I would like to explore more in detail, to find some hopefully physically relevant examples to which we can apply the techniques you have shown us to try to get relevant results, let us say, okay? In principle, I mean, I think that the rest is, I have not followed all the details, but I trust you, and I'm sure it is everything is well done. But I don't know if you have experience in applying that to concrete physical or problems, or if this is a quite open question now.
Well, as an application, we worked on the one-dimensional hydrogen atom, the so-called one-dimensional hydrogen atom with the Coulomb potential 1 over absolute value of the distance from the origin. We studied the long-standing questions about the fundamental, the ground state of this system, and I think that this approach solved some of these questions, but except for this problem, we didn't work it on models. This last result, by associating physical parameters, the so-called physical parameters, was just obtained by us, and we had not still published this paper. We are submitting in the next weeks, but it will be applications which will be very welcomed.
Now that you will come here, you are also very welcome here to Valladolid.
Yeah.
Of course, I think that we will have the opportunity maybe to consider some of the problems that we have been dealing with, and to apply this technique to these or to some variants, and that may be an opportunity to work all together in those types of problems. Okay.
Yes, I think
this
it
is
will
an
be
idea. I
very
don't know what
interesting.
Manolo thinks about that, because probably he has some other ideas in her big mind, but that could be a possibility too.
Ok. Allora Silvio, adesso tocca a te. Scusate, ma anch'io ho qualche piccolo problema. Spero di riuscire a mettere il PDF di Silvestro.
3 minuti perché io devo andare al bagno.
Ok, let's see. No, this one. Annulla. Ok.
No.
Silvestro, vedi? Lo vedi il...
Perfetto, sì, perfetto.
Ok, allora, Silvestro sostanzialmente, parlo qui, questo è un lavoro congiunto appunto con il gruppo spagnolo, al quale ancora sono molto grato per essere intervenuto oggi, e sostanzialmente, ecco, vedete il titolo del lavoro, On the Hamiltonian Describing Two Attractive Non-Local Delta Prime Interactions with Equal Strength Symmetrically Situated about the origin and its behavior as the distance between the two centers vanishes. Ma senza entrare troppo nel dettaglio, io lascerei la parola a Silvestro a proposito, se lui mi dà l'ok, di una questione che emerge appunto dal lavoro.
Let's first go to page 2.
Page 2.
Andiamo
Okay.
a pagina 2 prima.
Sì, ok. Tu mi dici e io ti seguo. vediamo un pochino, intanto se si vede, perché qui pare che non abbia caricato. I don't know what's going on. Perché? Che succede? Come mai non lo vede? Un attimo, questo è, facciamo così, questo lo chiudiamo. Allora, facciamo così, magari lo riprendo. Questa è la diretta YouTube. La riapro, Silvio, un attimo.
Sì, sì.
Ok. Vediamo un po'. Mi pare che adesso ci siamo. Uno. Ok. Dove vuoi che mi... la faccia un po' più... Questa è la pagina 2.
Pagina 2, perfetto.
Aspetta Silvio, la faccio più piccola, riesci a vedere?
Sì, 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 sì.
Allora, dimmi... Ok. Fai una... Considera... abbiamo 25 minuti, insomma all'una poi dobbiamo lasciare la sala, quindi vai subito, come si dice, al nocciolo della questione, fai una breve introduzione e poi vai alla questione di cui abbiamo discusso anche nei giorni precedenti. Ok, ti lascio la parola, vai.
Grazie. One of the main themes of my research work on point interactions over the last 13 years has been the so-called coalescence problem. That is to say, you start with a pair of identical point interactions, and you start shrinking the distance between them, and you studied the behavior of course, as perturbations of a given free Hamiltonian, and then, of course, you analyze the behavior of the limiting operator. This work started 13 years ago with Fabio, and by the way, I should say that whatever I have been able to accomplish could never have been accomplished without the collaboration of with researchers such as Fabio and Stefano at Marconi and Lewis in Rome, my mentor Sergio Albeverio, and my friends from Castilla, Luis Miguel and Manolo. So I'm really grateful to all of them for their professional collaboration and even more for their personal friendship, which I value immensely.
Mm-hmm.
So,
grazie Silvio, thanks.
Here we focus on the so-called non-local delta prime interaction, which is essentially what Sergio calls, well, for the whole Hamiltonian with the non-local delta prime, which Sergio calls Hamiltonian with a singular density. So, as you can see on page 2, that is an even point interaction using the terminology introduced by Taddeo. So it's even because it is non-local, so you have two delta primes. If we can go back to, I don't see page 2 now.
Non vedi più pagina 2? E noi siamo su pagina 2. Aspetta, possibile?
Ma non la vedo.
Non la vedi? Adesso?
Yes, now, yes.
Espressione 2-1. Ok.
So, in an interesting paper by some awesome authors, the interaction was also called momentum-dependent interaction, and that is clear from the quadratic form as written in 2-2. So you have the non-local delta prime centered at the point x0. Of course, using basic distribution theory, you transfer the derivatives to the test function f. Then you have the non-local delta centered at x0 in the middle, but the non-local delta coincides with the local delta, so you get that. Now, if you have two of them, of course, a premise is important. In the majority of our works, we have always chosen the p-space representation, even though it seems to be less popular. But I think it's more transparent and more physical. So once you use the p-space, you can clearly see that what you get is a rank 2 perturbation, as shown by formula 2.5. So, as you know, a crucial operator when we deal with perturbations of the Laplacian or other free Hamiltonians is the so-called Biermann-Schwinger kernel, or Biermann-Schwinger operator, which has an integral kernel. So, because of trivial trigonometry, essentially the formula for the cosine of the difference of two angles, this Biermann-Schwinger kernel reduces to this Biermann-Schwinger operator reduces to a rank 2 operator because of cosine, cosine, sine, sine. And therefore, the explicit form of the Biermann-Schwinger operator for the non-local delta prime is given by 2,6. Now, you can immediately see the difference with the situation for the delta in 2,7. That is, in 2,7 you see the Biermann-Schwinger kernel for the delta. The problem is given by the presence of the p prime in the fractions to the left and to the right. So let's go to page 3. So it's well known that in the case of the delta, that kernel is trace class. That, of course, cannot happen in the case of the delta prime. The page again. Now, so it's well known that the delta prime, the non-local delta prime, is not in the class H-1 using the terminology of rigged Hilbert spaces, which should be very dear to Manolo, who wrote excellent articles with Enrico on rigged Hilbert spaces. So the non-local delta prime is not in H1, H-1. However, it is in H-2 because if I don't see page 3 anymore.
Oh, ma sei sicuro? Okay.
Now, yes, now I can see it.
Aspetta, 3, vuoi la 3 o la 4?
3. 3.
Eccolo.
So, slightly above, un pochino sopra.
Sopra.
So, now, if we surround the Billman-Schwinger of the non-local delta prime both to the left and to the right by means of the square roots of the resolvent in P space, then of course we get a kernel, the kernel of a trace class operator as the simple calculation of the trace shows in 210. So that confirms that the non-local delta prime is not in H minus 1 like the delta, but it is in H minus 2, using the terminology of rigged Hilbert spaces. That means that we need the so-called renormalization of the coupling constant to define the Selfadjoint operator, making sense of the purely heuristic expression.
Okay.
We carry out the renormalization of the coupling constant. So we start with the traditional ultraviolet cutoff of the momenta. Then we carry out, let's skip these details. So we carry out all the limits, and let's scroll down. Yes, formulae 214 and 215 are important because they define the coupling constant lambda of k, where k is the cutoff in the momenta. So we scroll down, we go to page 5, we carry out all the limits, and we reach the desired outcome, no, slightly above, un pochino sopra. So we get this limit for the inverse of the Billman-Schwinger kernel, 218. Now, what is the problem here? The problem is that the function inside the rank 1 operators are not in L2. So that is a problem, but it is not a real problem because that operator per se is not physically relevant. By referring to Tiktobler's formula, what becomes physically relevant is when we have that operator surrounded by the square roots of the free resolvent. So again, we use p squared plus absolute value of e raised to the -1/2, both to the left and to the right. And now in 219, we get a well-defined rank 2 operator perturbing the free resolvent. So that's it. That is the resolvent. That is the desired resolvent of the limiting operator. Well, there should be a technical proof in order to show that this limit is indeed the resolvent of a Selfadjoint operator. It's a subtle proof, but it is essentially identical to so many proofs for similar situations, so it can be skipped. So let's go to the next page with the desired result stated in a theorem. So that is the theorem. It is possible to define a self-adjoint operator making sense of that heuristic expression. The operator is the limit in norm convergence of the resolvents of those Hamiltonians with the cutoff. So once we have the explicit expression of the resolvent, of course, we can look at the poles along the real axis in order to study the eigenvalues. And now, those are the two equations for the eigenvalues, 3.1 and 3.2. And so in section 3, we began studying how these two eigenvalues behave if we keep beta, the strength of the interaction, fixed, and we let x naught, meaning half the distance between the two centers, vary. So, of course, thanks to Luis Miguel's excellent numerical work, here we have the plots on the following pages. Let's scroll down. So, of course, the red curve is the one depicting the ground state energy, whereas the blue one depicts the excited state energy for various values of x naught. Figure 1 for beta equal to -1/2. The second is for beta equal to -1. And for larger values of beta, -5 and -15 in the two figures of figure 2. So, they're quite interesting because you can notice immediately a very important property. So let's scroll down. So
okay.
The first property, which is shared by this singular double well with the one with two delta interactions, is that they have this sort of asymptotic degeneracy, because as you can see, when x naught becomes very large, basically the two curves almost coincide. So it is as if there were a single delta prime placed at plus infinity with an eigenvalue which is doubly degenerate. That is exactly the same situation with the delta. Let's move up to the previous page 1 second. It's the same situation we have with the delta. However, of course, these asymptotic values are quite different, because here in this model, the asymptotic value is -4 over beta squared, which is the eigenvalue of the delta prime, of the non-local delta prime. Whereas in the case of the double delta, the asymptotic value is, of course, negative lambda square over 4. So, I don't know whether it might be surprising or not, but they share this common feature. Another common feature is that the ground state gets less localized By the way, one important thing. This, the asymptotic degeneracy is also shared by another interesting model, meaning always this double well of negative delta, but added to the semi-relativistic Salpeter Hamiltonian, square root of p squared plus m squared. Of course, because of the free Hamiltonian, here, although we have two deltas, we do need the renormalization procedure to define the Selfadjoint Hamiltonian. Here we have the deltas, but the free Hamiltonian is not p squared, but it is square root of p squared. So also for this Salpeter Hamiltonian, we have the this asymptotic degeneracy, of course, to a different value. Another common feature is the positional disorder, meaning the ground state energy, the ground state is less localized as we move to larger values of x naught. So these are some interesting features. Now let's go quickly to section 4, where basically we
Silvio, abbiamo sorry, 7 minuti però.
6 minuti ho visto.
Sì, dobbiamo stringere un pochino.
So let's go to 6 then.
Ok.
So of course we are going to investigate also the problem of resonances. So now the interesting thing here is that in our previous papers, whenever we dealt with such singular double wells, requiring the renormalization procedure, so for the Salpeter Hamiltonian or for the double delta in dimension 2, dimension 3, with either the free Laplacian or the harmonic oscillator, we needed, in order to fix the coalescence problem, in order to make the two deltas merge smoothly, we needed to make the beta, the coupling parameter, we needed the coupling parameter to be dependent on x naught. That was the only way out. Otherwise, we did not get the smooth merging. Now, in the case of the double delta prime, quite surprising, quite a surprising fact, although we need the renormalization to define the delta prime, that is not the case, because the two delta primes merge smoothly, they coalesce to get a single delta prime interaction with double strength. And in section 6, before this final page 12, of course, there are the technical details of the proof that in the limit as x naught goes to 0, you approach the Hamiltonian of the Hamiltonian with a single attractive non-local delta prime centered at 0. So I can't see the page anymore, so
ora?
yes, exactly. Thank you. So I have the following question, food for thought. It seems rather surprising that two delta prime interactions, which do require the renormalization procedure in order to be added to the free Laplacian, to the free negative Laplacian, can coalesce smoothly as the distance between the centers vanishes. So I would like to get your conjectures, ideas regarding this paradoxical or bewildering phenomenon. My guess is the following. No matter whether we need renormalization or not to define the delta prime, the fact that we get the smooth merging is simply due to the fact that the operator converges in norm-resolvent convergence to the one of the single delta centered at zero. So because of a technical theorem, which is called a principle, which is called principle of non-contraction of the spectrum under norm-resolvent convergence, given that all those curves always end up at that precise value at x naught equal to 0, that eigenvalue will be extremely stable. So when we go to 0, that eigenvalue will stay there, which is not what happens for the ground state, of course, which disappears. So that is, that might seem mathematical, but in reality, I think it is physical, because the delta prime is astonishing, because its ground state is antisymmetric. Its ground state eigenfunction is an antisymmetric function, differently from other even interactions. So that is my educated guess. So maybe quickly, in a couple of minutes, I would like to have your impressions, your conjectures about this point. And thank you very much for your attention.
Ok, grazie Silvestro. Adesso vediamo se
Prego.
Taddeo ha qualcosa da dire a proposito di questo strano comportamento della delta prima, che in qualche modo inverte la situazione della delta e che trasforma gli stati da simmetrici a antisimmetrici. Lascio la parola a Taddeo, vediamo che ne pensa lui. What do you mean about this Silvestro's question?
Well, thanks, Silvestro, for your talk. Well, I have little to say, because I should enter in the spirit of your computations to grasp what's succeeding, but some of the results you mentioned are, it sounds a bit uncomfortable because are you using the delta prime, that usual delta prime, which I mentioned, which is an even interaction?
But non-local, meaning there are two of them. You saw the bracket.
Yes, but individually, the single ones are the so-called usual delta prime.
Let's say
Right.
that are Shevas delta prime.
See,
Right.
When some time ago, in a paper in 2016, following the approach of SIBA, two delta primes shrinking with renormalized coupling constants. And if I'm not wrong, we concluded that the lambda matrix at the shrinking point was dependent on the energy, and this was it was considered by us. It was considered by us as a non-admissible interaction, because when the lambda matrix depends on the energy, it implies that the singular order of the distribution is higher than the maximum allowable.
This is true. This is true, but
no, but here there is no dependence on the energy.
this
Yes.
this is true, but this is not
Yes.
the case here.
Sorry?
There is no dependence on the energy here.
It is for the derivatives the order 2 and higher, second derivatives and higher. This is true.
Yes, but when you shrink, when you start from two delta primes, which are singular order 1, and when you shrink in the resulting shrinked interaction seems to be higher order, and it will be not admissible according.
No, but I'm using.
Cut it. I didn't.
Silvestro, non si è sentito quello che hai detto. No, we
Ci ha
didn't hear.
tagliato.
No.
You're using the local delta primes.
Yes, but when you shrink, this shrinking procedure maybe is introducing a higher singular ordering, I guess. In our paper of 2016, we departed from two usual delta prime, which are admissible. But when we shrink with renormalizing the decoupling, we obtained at the limit a non-admissible in the sense that it depends on the energy. Non lo so.
Silvio, you are saying it's not depending on the energy.
I don't know how this
On the
results.
energy.
Sì, parla tu, di.
Because the eigenvalues depend only on beta, the coupling parameter, and x naught. And the upper one, the eigenvalue of the excited state, is extremely stable as we approach x naught.
You mean the first excited state is stable with respect to the ground state that disappear? But there is no dependence on the energy. This is the question.
That is
It depends only from x0 and beta.
no, I'm referring to lambda. The lambda matrix depending on the energy.
The lambda matrix, yes, maybe is a
Yes.
different approach. Maybe. Silvio, non può essere un approccio differente, quello che sta illustrando.
Io non riesco allora a vedere
A
la
focalizzare,
connessione,
certo.
perché avevamo lavorato già su queste cose,
Sì.
e il risultato era questo, che lambda dipendeva
L'ordine è
dall'energia,
troppo, sì.
e per questo l'abbiamo
Scartato.
sì. Ma forse possiamo aver dimenticato qualcosa. Queste sono cose da rivedere.
Silvio, però tu intendevi anche un aspetto puramente fenomenologico, giusto? Ne parlavamo qualche tempo fa, cioè chiedersi realmente che cosa implica da un punto di vista fenomenologico questa cosa. Ti ricordi? Cioè come può essere...
As I said, apart from the mathematical complications, I think the physically relevant fact is that with this non-local delta prime interaction, the excited, when you have the double delta, you have two eigenvalues. As you approach x naught, the eigenvalue of the excited state becomes the dominant one and the stable one. The one of the ground state of the with the even eigenfunction in the end disappears, because of course it goes down to minus infinity, but because of the principle of non-contraction of the spectrum, you don't get anything out of that. But the other one, the excited state, is extremely stable, and it is associated to an antisymmetric wave function. So it leads to a sort of quantum phase transition, because as you approach x naught, the symmetry of the ground state eigenfunction changes from symmetric to antisymmetric. So physically, I think it's quite relevant. So
forse possiamo...
Questo, cioè pensare a qualcosa di fisicamente rilevante dato quello che ha spiegato Silvio, capito? È più chiaro adesso?
Più o meno.
Ok.
Ma io posso provare pure fare con il nostro approccio vedere cosa si diventano questi due delta prime nuovamente, né, con queste nozioni adesso di simmetrie.
Poi potrai vedere questo lavoro, magari qualcosa...
Con i parametri fisici forse si può vedere
approcciare in altra maniera.
Esatto.
Io ringrazio tutti quanti veramente per essere qui sia fisicamente che virtualmente, per la gentilezza e perché insomma siete stati qui. Io ringrazio anche i miei due ospiti che hanno avuto una pazienza infinita, non si vedono ma ci sono, il professor Carlo Diazeolla e il professor Stefano Viaggio. Io li ringrazio infinitamente per essere intervenuti, speriamo che questa discussione sia stimolante per un futuro e speriamo magari un giorno di vederci tutti quanti insieme. Io ancora vi ringrazio di cuore e alla prossima, se qualcuno vuole dire una cosa. In Castiglia. Con un buon vino tinto. Magari. Ok. Allora, io di nuovo ringrazio Taddeo per essere intervenuto, ringrazio Silvestro, Luis Michele e Manolo e gli ospiti intervenuti ancora. Grazie veramente.
E io ringrazio tutti pure, principalmente Fabio e Silvestro per l'invito e spero di vedervi tutti a Valladolid prossimamente.
Grazie ancora. Ciao Silvestro, mi raccomando riprenditi, noi ci vediamo presto. Ciao Luis Michele, ciao Manolo.
Ciao.
Hasta luego, hasta pronto.
Hasta luego.
Hasta luego.
Ciao.
È finita.